Okay, I think we are ready to start. So first of all, welcome all of you. I would like to thank also to Aline Bornet, Christian Kaluse, Matthias to Arens to be here. We will be the main speakers of this webinar entitled Testing Materials for Energy Conversion. And let me introduce you briefly the agenda and the topics that we will cover during today. In the first place, I will, as I'm doing now, giving a welcome and introduction to this webinar and also to the speakers and the dynamic and a little bit how we are going to proceed with this webinar. Then I will give the floor 10 minutes to Christian to introduce the project and also to frame the main topic of this webinar, which is testing materials for energy conversion, that it will be introduced by Aline Bornet from the University of Bern. And she will be speaking about the main topic of this webinar, and then we will finalize the session with 10 minutes of Q&A, and also I will conduct a Mentimeter session to know the audience better and also to know a little bit more of you about who is watching our webinar. So just please, I would like to inform you that this session is being recorded and it will be shared on our social media channels as part of our dissemination strategy. So please make sure your microphone is muted. I think no one can activate it, but just in case, I'd like to remind of that. And also, please, if during the webinar you have any comments, question, or something that you would like to know, please feel free to use the chat tool to let us know your questions. And also, I don't know if you have used Mentimeter before, but that will be at the end of the webinar. We will conduct a session, an interactive session through this tool, and I would like to encourage you to use it to know a little bit more of you. So my name is Pablo Morales Moya. I'm a communications manager at Sustainable Innovations, and my role within the Recycalyse project is actually I'm in charge of the communication and dissemination work packages. That is basically to spread out the results and also to implement a communication strategy within the Recycalyse project. And some activities of my job is basically to celebrate or to organize this kind of webinars to inform not only the research and the industry stakeholders about the project, but also include or try to include more people that may be interested in this topic. I don't know, maybe Christian, I think it's better if you introduce yourself and tell us a little bit about you and your role in the project. So the floor is yours.
Thank you, Pablo. Yes, my name is Christian Kallesø. I'm a director at the Danish Technological Institute, and I'm also the coordinator here of the Recycalyse project.
And then we also have Aline Bornet. So Aline, if you want to say a few words.
Yes, hi everyone. I am Aline Bornet. I'm doing my PhD in the group of Matthias Arens at the University of Bern, and I'm part of the Recycalyse team.
Thank you so much. So I don't want to delay you, or I think, Christian, you can directly share your screen and tell us a little bit about the Recycalyse project.
Thank you, Pablo.
Let me stop sharing.
Yes, so you can see my screen?
Yes.
Good. Okay, yes. Thank you, Pablo. Yeah, as Pablo just mentioned, I will introduce our project. I will also talk a little bit about Power-to-X and electrolysis. And then after that, we'll move on to Aline and the subject of today's webinar. So we've all seen how the energy prices here the last 6 months or even more, including electricity, has gone up. And we also seen how the weather influences the price of electricity. The graph you can see here shows the solar energy production variation over the last year in Europe. And not surprisingly, we have higher production in the summer. If we will look at a similar graph for wind, we will see same variations over year and even over days. And for winter like this, we will have days where it's very dark, we have little sun, and we have no wind, and then of course we'll increase our gas consumption and hence the prices. If we then look into a future where we'll have 100% renewable energy sources, this variation in electricity production will become even more pronounced. So we need to look at how to store this electricity, this electrical energy for later usage. The graph here to the right shows an overview of various storage capacities for different energy storage systems. We have short-term storage technologies that can compensate for fluctuations that last a few hours, and then we have longer-term technologies that can bridge the gap over several weeks, maybe months, by storing the energy, for example, in hydrogen. We need both short and long term because we know that renewable energy can also vary over the course of a day and over the course of months. And if we want to store large amount of energy for more than 1 week, then we need to look into storing it in chemicals or fuels. And this is the heart of what we call power to X. It's converting power to something, for example, hydrogen. This figure here to the left, this shows typical pathways for power to X. So we start with renewable energy. Then we use that to split water into hydrogen and oxygen. This is called electrolysis. The hydrogen is, as the graph to the right shows, a very good energy carrier, but it can also be further synthesized into e-fuels, chemicals such as methane if you use captured CO2, or ammonia where you use the nitrogen from the atmosphere. These fuels and chemicals can then be used instead of fossil fuels in the industry, in agriculture, in transportation, district heating. You can maybe also use it to convert back to electricity. The heart of power to X, you can say, is really this electrolysis on converting renewable energy into hydrogen. And there are several, at least 3 different types of electrolysis. These are shown here. You have proton exchange membrane electrolysis, alkaline electrolysis, and solid oxide electrolysis. And there are pros and cons for all of them. Our project is focusing on PEM, and the advantages here is the dynamic operation ability. So we can easily adjust to a sudden decrease or increase in power. It's very efficient, so we waste very little energy. We can run at high current densities, and then we can reduce the operational costs. We have the ability to produce hydrogen at a high pressure. We can operate the system at high pressure, so that means that we can save some compression steps. We have a very high gas purity of the hydrogen that we produce, and we only use clean water, so it is fairly safe. This all sounds very promising, but of course there are also drawbacks, and these relate to the materials required for the conversion to be efficient, mainly for the catalyst. So the process uses critical raw materials such as ruthenium and iridium for its catalyst materials, and they are very expensive. They emit huge amounts of carbon dioxide when mined, as you can see from the table. And we also see supply problems in the future because we simply don't mine that. We don't mine very much iridium and ruthenium a year. So even though we use very small amounts of these materials, we still need to reduce the usage of these materials for the technology to become sustainable and economical viable. And that leads us to our project and what we look at here. So we have two main objectives, and that is to reduce, maybe eliminate the use of critical raw materials for our catalyst, but also to recycle the materials, and especially the critical raw materials that we might still have to use, so we can keep them in the value chain loop. And of course, it is to achieve our goal, which is to overcome the main existing barriers for PEM electrolysis, which is namely price, accessibility of the materials, and performance of the materials. If we then look at the concept of our project, which is illustrated here, then we look at new catalysts, we look at how to produce new catalysts, And then we look at how to integrate it into electrodes, into devices, into stack, utilize the materials in the stack in an electrolyzer. Then we look at the materials after end of life. So how can we recycle materials, maybe even upcycle it to save some production steps. And all this, we are 10 partners who are looking at. So just to go through it briefly, DTI, where I'm from, we are coordinating the project. Then we have TWI from the United Kingdom, TU Freiberg from Germany, Sustainable Innovations, where Pablo is from Spain. We have Prufex from Germany, Agorec from Germany, University of Bern, where Aline and Matthias are from Switzerland, Blue World Technologies from Denmark, and Hysenta from Austria, and then Fraunhofer ICT from Germany. And all of us, we are looking into how to come up with new materials, how to fabricate materials, how to fabricate electrodes, demonstrate materials and the stack, and then looking into how to, into the circular economy, how to reuse the materials. Of course, then what Pablo is doing is how to communicate what we're doing and then to look at the business development. And if we go a little bit more into details with what's actually going on in these various areas, then within materials, we are looking at new alloys. First of all, can we completely use new alloys without critical raw materials? And if not, how can we alloy the critical raw materials with some other elements to boost the activity? And then we use it then we look at how to utilize support structures. So the small illustration here is to have catalyst, very small catalyst particle on a little bit larger support particles, so we can lower the volume of the catalyst particles, but increase the surface area and then hence boost the activity. And combination of alloying critical raw materials with nickel together with using a support structure called antimony doped tin oxide, we have actually shown a factor of catalyst activities which are 100 times better than commercial alternatives, which will allow us to reduce the amounts of catalyst used in the demonstrator. A big part of material development here is, of course, also material testing, which Aline will talk about in a moment. We also look at how to fabricate materials, fabricate the catalyst. We want to be able to produce at least 50 grams an hour using flow synthesis. Then we look at how to fabricate the catalyst inks that we are using to deposit onto electrodes to produce membrane electrode assemblies. They are tested in single cells, and these MEAs, membrane electrode assemblies, they are then also integrated into the stack where we stack several MEAs together to produce hydrogen. The challenge here is to optimize the fabrication process and the inks so we can really utilize the catalyst activity that we have achieved of the catalyst. And then we look at the demonstration. The stack is implemented into a system where we have optimized a lot of things through extensive simulation work. So the stack is, you might see on the picture here on the top right, is really only a small part of the entire electrolyzer. So a lot of optimization goes into the demonstration of the materials. We then have a lot of partners looking into the circular economy, how to reuse and recycle materials. We look at how to optimize the disassembly process of the stack, so we can divide it into electrodes, titanium plates, and so on, and then automatically picking up MEAs for recycling. And then we look at how to recycle the materials within the MEA, so we need to separate it then before we can leach out the critical raw materials into solution, and we can then separate it using various methods, extract it, phase separate it, and then we can dry it, and then we have pure raw materials on precursor form that we can use for catalyst production again. And then you can see the loop. And then another important part of this circular economy work is our work within life cycle analysis, the life cycle costing, and the social life cycle analysis, which feeds in to all different parts of our project for making it as sustainable as possible. And then, of course, the outreach and business development part of the project is also important, and Pablo is in charge of both communicating through videos, having webinars like this, different outreach activities, and then also look at exploitation of our results. And With that said, that was it for me. So we'll move on to what it's all about today, which is Aline and testing materials for energy conversion. Thank you.
Thank you so much, Christian. So I think we have something on the chat before moving maybe to Aline.
Sure.
I think it's just people saying hi.
Yes, it's actually just hi.
Hi.
Then Aline, the floor is yours. If you have any further questions, we will have a final Q&A at the end of the webinar.
Okay, thank you. So you see my presentation?
Yes,
Yeah.
it works.
Okay, perfect. And the pointer. Good. Then good afternoon, everyone. Welcome to my part of this webinar, where I'm going to present you the result I obtained so far during my PhD. But first, let's have a quick overview on the different work packages of Recycalyse. And our group at University of Bern is leading the early work package 2, and we are also working on the work package 4. And today I am going to mainly focus on the results obtained in the work package 2, where we are not only working on the development of highly active catalysts, but also on the development of suitable screening methods. And basically, this is what my talk will be about. I'm going to first start with the catalyst synthesis, and then I will follow with the description of different screening methods. One is the inverted rotating disk electrode, and the other one is the gas diffusion electrode. And I'm going to end the presentation with a short conclusion. So let's start with the synthesis of our catalyst. And as mentioned before by Christian, we are using iridium and ruthenium, as this is the state-of-the-art metals for the oxygen evolution reaction. The synthesis follows a surfactant-free colloidal approach, where the dissolved precursor salts are mixed with alkaline ethanol and heated under reflux. Once the metallic nanoparticles are formed, they are mixed with the support, either carbon or antimony doped tin oxide, ATO in short. Then the solvent is evaporated, and I obtain this catalyst powder of either iridium or ruthenium, of either iridium or iridium ruthenium on either carbon or ATO, all of them with a nominal metal loading of 58%. This means that the catalyst is composed of 50% of nanoparticles and 50% of support. Then this powder is dispersed in a solvent mixture, and I obtain a stable dispersion. This is the stability of this dispersion is an important property, as we will use it later to prepare of our electrodes. We then perform some characterization of the nanoparticles, first by means of TEM, and we could see that the nanoparticles are spherical and that they are better dispersed on the ATO support than on the carbon, where they are formed small aggregates like here. Then the mean particle size was also determined, and it is about 1.5 nanometer for the 4 composition. EDX was also performed to determine the elemental ratio between iridium and ruthenium, and it is about 40 to 60, and this is regardless of the support. And finally, SAS or X-ray absorption spectroscopy measurements were performed to identify the nature of the iridium-ruthenium catalyst, and it was found that the nanoparticles are an alloy, and so that they are not segregated particles. The next step is to test the performance of the catalyst, and for that we need an adequate method. Nowadays, rotating disk electrodes are the state-of-the-art setup to test the performance of the catalyst in the labs. In such a setup, the catalyst is deposited with a low loading on a disk, which is rotated in an electrolyte. This is a suitable technique when the product of the reaction are soluble. However, when we are working with gas evolving processes like us, it is highly questionable. Indeed, the down-facing configuration of the setup does not allow the gaseous product to escape the surface of the catalyst. And thus, the formed bubbles are accumulating on the electrode and blocking the active sites. Moreover, if we want to analyze quantitatively the product, it's become challenging to collect all of them. Actually, the limits of the RD setup are being recently more and more addressed in the different publications. And here is one example. In this paper, the authors applied constant current on their iridium on ATO catalyst and recorded the potential. And as a quick reminder for you, the higher the potential at a fixed current, the worse is the catalyst. So here, if we have a closer look on the D plot, where a current of 27.5 milliamp per square centimeter was applied, we can see that the catalyst loses its activity in the course of the experiment, as higher potential are recorded. And this was explained by a slowly covering of the catalyst by bubbles. We performed a similar experiment, however, without rotation, to emphasize the massive accumulation of bubbles. And on the right graph, we can observe also this increase of potential over the time of the reaction. We also recorded a video where we can very nicely see the formation of the oxygen bubbles. The parts that are covered by bubbles, so here, for instance, are no longer contributing to the reaction. This means that the uncovered part here are more and more stressed, and that is why we see the increase of the potential. So definitely, this setup is not suitable for the oxygen evolution reaction. A simple and elegant solution to solve this buoyancy problematic is to rotate the setup by 180 degrees. With this upward facing configuration, the formed bubbles can finally escape the catalyst surface and reach the electrolyte surface. This was actually proposed 30 years ago, but never really implemented for gas evolving processes due to technical challenges. Until these guys from the Berkman group, also at the University of Bern, designed this so-called inverted RDE. The novelty of their setup is that it is hermetically sealed, and so it was possible for them to couple it to an online gas chromatograph, and so directly analyze the gaseous product. This inverted configuration was already used to study, among others, the hydrogen evolution reaction and metal deposition. And now, in collaboration with this group, we are studying the evolution reaction, oxygen evolution reaction. So let's start by comparing both setup, and in both cases, I'm using the iridium on ATO catalyst. So let's start first with the results obtained with the traditional configuration. And for that, I casted the ink dispersion onto a glassy carbon, and I cycle it between 1.2 volt and 1.6 volt at 2000 RPM with a scan rate of 10 millivolt per second. And we obtained the current as a response. On the left-hand side graph, the forward scans of the CVs are plotted, and on the right-hand side plot, we can see the evolution of the current density over the different cycles at a fixed potential of 1.55 volt. And we can clearly see a decrease in the current density over the time. And the question is why? In the literature, the decrease is often attributed to activity loss, but is actually, as we saw it before, It is due to a massive accumulation of oxygen bubble on the catalyst surface. So we can clearly see here on this picture. Then we did the same experiment with the inverted setup with a fresh electrode. And the question now is, how is the evolution at this potential of 1.55 volt? And we see that the evolution is not the same, and we don't see this rapid decrease as we saw it for the traditional configuration. We observe instead rather plateau-like behavior with some jumps and oscillation that corresponds to bubble detachment. And this can be very nicely seen in this video. We see the bubble is formed and poof, it gets detached from the surface of the electrode. And this video corresponds to the scan 17 and 18, and we can see it also on the forward scan. Here, shown by this arrow, we see an increase of the current density, which corresponds to the bubble detachment. So as a first short conclusion, we could see that by inverting the traditional RDE by 180 degrees, the bubbles are no longer an issue for our OER measurements. We finally have a setup for testing the performance of OER catalyst in a quick and reliable way in the labs. In Recycalyse, we want to move a step forward in the testing of the catalyst. We want to apply conditions closer to the real electrolyzer, so it means that we want to go from basic science to a more complex and technological relevant system. Unfortunately, this cannot be achieved with this inverted RDE, as only thin catalyst film are used, and this catalyst is in direct contact with the liquid electrolyte. A setup that uses thicker films and does not have a liquid electrolyte is the membrane electrode assembly, or MEA in short. In such a device, realistic conditions can be achieved. However, it is a quite complex system and therefore time and resource consuming, and so not every lab can afford working with it. Therefore, we need a bridging tool that enables fast and straightforward measurements under more realistic conditions. And at University of Bern, we have such a setup, and it is called the gas diffusion electrode setup, or the GDE setup. This testing platform is a good compromise between the simplicity of usage of an inverted RDE and the possibility to reach conditions closer to MEAs. The setup was first introduced for fuel cell testing, and now we are adapting it to test the water electrolysis. So let's have a look on that part where all the magic happens. We see that it's a 3-electrode system with the catalyst being our working electrode. We have a counter electrode, which is a platinum mesh, and the reference electrode. The electrolyte is a 4 molar perchloric acid, which is separated from the catalyst by a membrane. So we don't have a direct contact. And all of this works like this. Once the reactant, the water, reaches the catalyst, it oxidizes to oxygen, which leaves the cell, and to protons, which pass through the membrane and reach the cathode, where they are being reduced. So now we need to prepare the working electrode, and this is done via vacuum filtration approach. During this approach, the catalyst is deposited on a transport layer. And this transport layer needs to be porous to allow the reactant stream to reach the catalyst. We started by using a carbon-based transport layer as it is commonly used in the fuel cells. And after deposition of the catalyst, we obtain such an electrode, and here you can see a cartoon of it. We have the carbon fibers of the transport layer, and this is the porous network. Sorry. On top of it, we have the microporous layer, MPL, and this prevent the penetration of the catalyst into the fibers, and on top of it, the catalyst itself. And in reality, it looks exactly the same, and we can see it in this cross-section SEM image. We can see the carbon fibers, the MPL, and on top of it, forming this brighter layer, this is the catalyst. And we perform some EDX mapping, and we can clearly see that iridium and ruthenium are forming a homogeneous layer on top of the MPL, and they are not all over the transport layer. And so we use this electrode in our GD setup, and we tested the performance of the catalyst first in terms of activity. This was done by stepping the current at different values every 5 minutes at 3 different temperatures, 30, 40, and 60 degrees. Moreover, for each temperature, triplicates were measured to ensure the good reproducibility of the experiment. On the A graph, we can see the response of those current steps for the iridium-ruthenium catalyst. We can see that during the first step, we cannot reach a steady state behavior. And this is due to an ongoing oxidation of the catalyst. So during this step, we are going from metallic catalyst to an oxide catalyst. After these steps, the catalyst reaches a steady state behavior. And in the B graph, the so-called Tafel plot is represented. This means that the log scale of the applied current is plotted against the potential. We are expecting to observe a linear behavior if only kinetic processes are happening, and we see that it is the case where the catalyst reaches the steady state behavior. Furthermore, on both graphs, we see that at higher temperature, the catalyst becomes more active, and this is expected from kinetics. We did the exact same current stepping experiment for each catalyst, and we compare them on those bar diagrams where the current density at an overpotential of 230 millivolt is plotted. This overpotential was chosen as it lies in the linear Tafel region of the all individual catalysts at most temperatures. The full bars correspond to the nanoparticles deposited on carbon and the dashed one on ATO. And on the left-hand side of each graph, it corresponds to the iridium nanoparticles, and the right-hand side, it's the iridium-ruthenium nanoparticles. Okay, so what we see here is that ruthenium-containing catalyst exhibit always a higher activity as compared to the pure iridium. Then we also see that the nanoparticles deposited on carbon always shows a higher activity. And finally, we see that the ATO becomes less performant at a higher temperature. And this is the first hint that ATO support might causes problems at elevated temperatures. And then we wanted to test the stability of our catalyst, and we did it by holding the potential at 1.6 volt for 2 hours at 60 degrees. So this is quite harsh conditions for the catalyst. Unfortunately, we could not conclude so much out of these experiments, as all catalysts degraded within the first 30 minutes. We wanted to believe that it's not our catalyst that is performing so bad, but that is rather something else causing this loss of activity. And actually, this something else might be the transport layer itself, as it is carbon-based, and it is well known that the latter is not stable under the harsh OER condition. So to test this hypothesis, we decided to use another transport layer, namely a titanium-based one, that is also called PTL. We use this one as it is commonly used in the PEM electrolyzer. In other words, we want to change this to carbon-based part by a titanium based one. And to do that, we had to rethink our way of preparing the working electrodes. As this titanium-based transport layer do not have the MPL, and so we cannot use the vacuum filtration approach. So we used the so-called catalyst-coated membrane approach, or CCM approach, where the catalyst is first sprayed or deposited on the membrane and then hot pressed on the transport layer. And in my case, it looked like this. We used the Nafion membrane and we sprayed the catalyst with a spray can, and then we hot pressed them onto the titanium transport layer. Then I used one of these electrode and I compared them to the carbon transport layer with the same catalyst. And I compared them using this following protocol at 60 degrees. First, the activity was screened as before, so we step the current at different values every 5 minutes. Then comes the stability step, where the potential was held at 1.6 volt for 2 hours. And finally, we repeated the activity step. And in the following slide, I am going to compare the beginning activity to the end activity. So let's start the comparison with the carbon-based transport layer. And here you can see its beginning activity, which is not too bad for a catalyst. Then if we go through the entire protocol, we can see that the gray curves are not in line with the black ones, and that they are reaching fast high potential, which means that the catalyst has degraded during the stability step, as higher potential for the same currents is an indication of bad performing catalyst. So this is actually expected from the previous results. The catalyst on the carbon transport layer completely lost its activity at the end of the experiment. Then moving forward to the titanium-based electrode, we see that the beginning activity, so the red curves, are in line with the black ones. This means that both electrodes give similar activity, which is expected as the same catalyst is used, and the transport layer should have a minor effect on the overall activity. Then this time, going through the entire protocol, we clearly see that the end activity is almost the same as the beginning activity. The small difference might be attributed to the ATO instability at elevated temperature, as I already pointed out earlier. And so here we can conclude that the carbon transport layer is not suitable for stability measurement, and that titanium transport layer should be used instead. And as a final experiment, we compare how suitable is our GD setup compared to the traditional configuration of the RD setup for stability measurements. And for that, I reused this publication where the authors saw an activity loss of after 30 minutes for a constant current of 27.5 milliamp per square centimeter. And under similar condition in our GD setup, our catalyst deposited on the titanium transport layer is stable for 2 hours of testing. So we can conclude here that the GD setup combined with the use of the titanium transport layer is suitable for stability measurements. And this makes a nice end to this presentation, where I introduced you to the revisited configuration of the traditional RD setup. In this new configuration, the setup is rotated by 180 degrees, which allows the bubbles to detach from the electrode surface, as you can see it here one more time on this video. And therefore, we can say that that with this inverted configuration, the buoyancy problems that the traditional configuration face are solved. And this setup is adequate for fast performance screening in the labs. But if we want to reach conditions closer to the real application, as it is the case in Recycalyse, we need to use the GD setup. And this is a suitable bridging tool between this inverted RDE and the MEA. It is quite simple to use, and still it can achieve conditions closer to the electrolyzers. And there I compare two options for the transport layers where the catalyst is deposited onto. And one is the carbon-based and the other one is the titanium-based. And we saw that the preparation of the electrode is feasible for both. However, it's a bit more easier for the carbon-based as we only need the vacuum filtration setup. Then we see that both transport layer are, with both we can determine the activity. However, if we want to determine the stability of our catalyst, we have to use the titanium-based transport layer as the carbon one is degrading in the course of the measurements. And with that, I am at the end of this presentation. I hope you enjoyed it. And I still want to thank all the Recycalyse team, as well as the group in Bern and our collaborators. And of course, you for your kind attention.
Thank you so much, Aline, for sharing also nice pictures. I think, Matthias, you have your hand raised. I guess you want to say something?
No, sorry, that should have been a clap. Wrong button, sorry.
Okay, no problem. Well, Aline, we have a few questions from the audience. Let me read. The first one is, are the IRDE setups commercially available?
No. So this was, actually this was a prototype from this Breukman group. And until now, I think they don't commercialize it yet, maybe in the near future, I don't know. But I guess you can read the publications to and contact them if you are interested in a collaboration with them.
Okay. Also, we can also type our emails in the chat in case you want to ask something specifically. So I encourage you to also reach us through email. We have two more questions. One is referring the slide 6, in case you want to move to the slide 6. It says, why are you showing in slide 6 RDE experiments but without rotation?
Wait, I did something and now I don't know how to go back to.
Oh, you need to share the screen again.
Let me. Yeah. Okay. Sorry, I will share. Sorry for that. Do you see it?
We see the. I can.
You see the presentation mode? Like
no,
this?
we see the demo. Now we can see it.
Okay. Okay. Sorry for that. Let me go to slide 6. 6 here. Yeah, this is a good question. We didn't rotate it because we wanted to emphasize this accumulation of bubbles that are blocking the surface of the catalyst. Basically, that's why.
Okay, and we have the last question is, have you tried working with less precious metals like MnOx?
Yeah, manganese oxide. Yes, actually, this is a part of the Recycalyse project, is to go from critical raw material to non-critical raw material. And we have tried some experiment with this manganese oxide combined with cold nanowires. And we could achieve quite high current, but at quite high potential. And this non-critical raw material are not really stable under these harsh OER conditions. So we are still trying to figure out a suitable catalyst that is not made of precious metal.
Okay, I think there is no more questions, but please, I encourage you to ask anything you may be interested. Okay, so then let me share now the screen. As I mentioned in the beginning, I would like to conduct an interactive session. So as I mentioned, I don't know if you have used Mentimeter before. You just need to grab your phone or maybe your computer, www.menti.com, and then you need to introduce this code 35. Let me also copy in the chat in case you want it. And I will give you a few more 1 or 2 minutes to get into the Mentimeter. Now in the chat you will see the code, and once you enter the code, you can answer the first question, which is, what country are you from? So we see that we have people. You can see the screen, right? The answers. Okay, so we have people from Denmark, Poland, Spain, Slovenia, Germany. Okay, more people. It seems that the majority of the people are from Denmark, Switzerland. Yes, the size also changed depending on the number of answers. Great, we have 18 answers. Maybe someone else can want to participate. Okay, I think most of the people are from these countries. Oh, we have from India also. Someone in the chat, it says that they are coming from Italy, Iran. Okay, good to see that we have a lot of countries interested in this webinar. So I think we can move to the next question. Which is, what industry do you work for? Again, this is like a word cloud. You can just type your industry and we will see, okay, we have research, science, university, or recycling, academia, which is basically the same that research. Oh, okay, it's moving a lot. I guess we have a lot of answers. Okay, so it seems most of you are from the university or academia. RTO, Tesla. Okay, good. Great. We can wait to see if anyone else can answer. But I will say that most of you are from academia, research. Great. Okay, so moving to the next question. We have also in the chat people saying energy and sustainable development in university. Great. I think we can move to the next question, which is, which technology do you work with? Fuel cells, battery, computer, hydrogen production, proton exchange membrane electrolysis, catalyst. Okay, it seems a wide variety. Okay, there is a lot of more answers coming. Let me see if I can read it. Iridium catalyst, water electrolyzer. Okay, great. Let's see if someone else. Green fuels, PVD sputtering, power to X, green fuels. Okay, so I see a lot of technologies. Maybe some of them are related. Okay. So let's move to the next question. Again, thank you for all this valuable contribution. We like to know our audience. So next question is, how useful did you find the content and the talks idea? So we would like to rate the level of quality or the level of satisfaction that you have with the content of this webinar, because it helps us to also improve the content of our webinars. So by the moment is 8.9, which I think is a very nice number. So thank you. It's good to see that it's been inspiring for you. The topics. We have 21 votes. I will wait a few more minutes because I'm quite interested to know your opinion on this. Okay. 8. So, okay, so also I encourage you, if you want, if you would like to know something more, or if you think that we should have included something else, we are open to new ideas or comments. So you can let us know on the chat, or maybe on our email account. You can also write us on there. Okay, so moving to the next question. I think there is one more or two more. Yes, two more. Are you likely to use this information in your future work or studies? Okay, so it seems yes. Again, if you think that it's not useful for you, it will be interesting to know the reason why it's not useful, or if you have missed any information or something, or it maybe is not applicable to your work or studies, but it will be nice to know also the reasons behind. Okay, but I see that most of you will use this information for your work or studies, so it's good to see these results actually. Okay, I don't know if we are missing any other answers. If not, I think we can jump to the last question, which is, would you be interested to know or collaborate more about the Recycalyse project? Here you have a few options. Okay, so we see nice results. So feel free also to contact us in our website. We have mail form where you can actually write us. Okay, good. Nice results. I'm glad to see that you are interested in the project, and you will maybe also like to collaborate or to know more about something in specific. I will go back to the presentation. I guess that you can see the presentation, right? Okay. So here, as I said, here you can find our mail, info@recycalyse.eu, where you can maybe write us if you have any questions, or you would like to know something else, or you would like to collaborate or something. We still have 5 more minutes. I don't know if you have any other questions or something that you would like to ask or to know from our speakers. Let me open the chat for the questions. Yes, we have one question for Aline. It says the carbon transport layer is not stable due to the degradation of the carbon. Therefore, what is the purpose of IR and IRRU supported on carbon materials?
Yeah. So we think that the carbon support is a good support to have first information of the activity of the catalyst. But later for the commercial use, maybe it's not the best one indeed, but for the first activity or testing in the labs, it's still suitable, as we saw it, that it gives better results. or
If I may add, then yes, this was like a beginning support right before we had developed the ATO. So so all the catalysts that we integrate in the stack is not with carbon, that's with ATO.
Okay, good. Well, there is, okay, another question. What commercial supports are available?
So we can find the carbon one and the ATO also. Here in this study, I used the a commercial ATO support, and else, honestly, I'm not sure about this. But both carbon and ATO for sure, we can find them, and the rest, I don't know. I know it exists also instead of antimony to put fluor or indium, but I don't know if we can find them commercially. I guess yes. But...
No, in general, working with supports for PEM catalysis is not that common, so that's why you don't have it. But you can find commercial, as Aline said, you can find commercial ATO, which in the end didn't suited our purposes enough because the conductivity was simply too low. And that's why we developed our own. So just going out and buying some commercial supports might not be an option.
Okay, I think we can answer one more question. Do you know why IR-ATO performances decreases with temperature compared to IRC?
So this is actually an ongoing debate in the literature. Some are claiming that the ATO is also lose its performance in the course of the experiment because we have antimony leaching during the experiment. And actually, we also think so. So probably it's this instability of the ATO that caused this decrease of performance at higher temperature.
Okay, so there is 1 minute less. So thank you so much. I would like to thank Aline, Christian, and also Matthias to be here, part of our team speaking today. So thank you for supporting me to celebrate this webinar. I think we really had a very nice number of attendees, around 61. So that's a very nice number. I just want to basically thank you all of you also to attend this webinar. And in case you want to see again this webinar, as I said in the beginning, the webinar is being recorded, and I will share soon the recording of the webinar on on the Recycalyse website, and also I will share it on social media. So I invite you to follow us on LinkedIn and on Twitter, to make sure that you don't miss any upcoming webinar or any relevant news concerning the Recycalyse project. So that's all from my side. Thank you all of you again. It's been a pleasure.
Thank you.
And stay tuned and
Thank you.
let's see if
Bye.
we organize more webinars. For sure, we will organize another one. So thank you so much. Thank you, Aline. Thank you, Christian.
Thank you.
Thank you, all of you.
Thank you.
Bye.
Bye-bye.